Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Haziqah Binti Zaifuddin. I'm going to present my final year project entitled Performance Evaluation of an Electric Vehicle in Real Operating Condition with an Internet of Things IoT-based motion sensor. My supervisor is Dr. Khairul Anuar bin Mohamad, and my panels are Dr. Siti Emily Binti Jumaat and Dr. Ahmad Fateh bin Mohamad Noor. As introduction, improvement of environmental awareness has led to shifting towards the use of electric vehicle technology that is much more environmental friendly compared to the internal combustion engine. Thus, the EV are evaluated for their battery level and trip distance and analysis of the battery consumption on distance, time, temperature, and load weight. This generates an insight in the mapping of the consumption for electric driving. There are a few problem statements. First, there are less proper research of EV performance in Malaysia culture. Second, automobile manufacturers are reluctant to release the private protocol of onboard diagnostic (OBD) ports to the public due to intellectual property and vehicle safety. And third, manual evaluation of EV is tricky and may cause injury and inaccurate data collection. Therefore, the developed system design will support this research for logging a large amount of data for the EV performance evaluation. There are three objectives in this project. First is to identify and analyze the factors and parameters that are affecting EV performance as a function of battery consumption. Second is to develop a data logger system to monitor the EV motion on road gradients through IoT platform. And third is to analyze an EV parameter through the developed system using a data analytical tools. For the scope, first, the type of electric vehicle used is battery electric vehicle or BEV. And the condition for testing and analysis the EV parameter includes multiple types of routes, which are roadway and highway. Third, the Node MCU as a microcontroller is used with Google Sheet IoT cloud platform to measure the parameter during testing on different types of road gradient, which are the uphill, downhill, and flat road by using the motion sensor developed. And fourth, the data analytical tools will be used are Excel and MATLAB. This is the overall flowchart for the project implementation, which consists of manual assessment and using a system device. First, for the manual assessment, I have performed multiple procedures of on-road testing and then collect data available parameter on vehicle's dashboard before making analysis on the parameters such as trip distance, time, weight, temperature, and speed. For the assessment by using a system device, I first developed onboard motion sensor by using an accelerometer and then perform multiple procedure of on-road testing, and then the data of acceleration and gyroscope are collected through IoT-based data logger system, and then the performance and data analysis on the driving behaviors such as accelerating, decelerating, and heading direction changes are made. For the manual assessment, the analysis was made on three different tests. First is the roadway, second is the highway short distance, and highway long distance. Throughout the test, parameters such as temperature, speed, battery percentage, and trip from the EV dashboard were monitored. For the first 40 km roadway test, the first evaluation, with maximum speed of 60 km per hour, EV can run at maximum 500 km range per one cycle battery. And the battery consumption also slightly increased with increasing environment temperature, but doesn't show much significant impact. For the second evaluation, with variation speed of 60, 70, and 80 km per hour, the battery consumption increased with increasing speed over trip distance. Second is highway short distance from Tol Plaza Air Hitam to Tol Plaza Tangkak. The first evaluation, speed variation is 80, 90, 100, and 110 km per hour. And the result shows that battery consumption increased with increasing speed over distance. Second evaluation of load factor parameter, the battery consumption increased 0.08 kWh per 100 km with increasing 1 kg load. Third is highway long distance. The test vehicle used are EV BYD E6 and internal combustion engine car Proton X70. Both cars are maintained at the speed of 90 km per hour from RNR Sedang to UTHM. For the evaluation of highway test field, the EV Sedang being compared to the ICE car. With the same average speed and total distance, the EV cost is only RM 4.19 cent and the ICE is RM 19.74. Here we can say that the EV is much more cheaper than the fueling price of ICE. The second method is using motion sensor with IoT-based data logger system to collect accelerometer data through Google Sheet Cloud. This then can be converted to CSV file. The acceleration and velocity was then produced using vibration data toolbox. The aim of this assessment is to identify driving behavior of EVs such as accelerating, decelerating, or turning direction on different road grade. This is the block diagram of the developed system, where the motion sensor will provide straight-axis gyroscope and three-axis accelerometer data. Then the MCU will transmit sensor data to IoT platform, which is the Google Sheet Cloud, where we can monitor through phone or desktop. And this is the circuit configuration, where the LCD will display the three-axis X, Y, Z inclination angle. And this picture shows the motion sensor is placed on the top of the vehicle dashboard, where the y-axis is aligned so that it is parallel towards the forward direction of the vehicle. Using the motion sensor developed, analysis was made on the acceleration of static angle on single, dual, and triple axis, the acceleration and gyroscope output, and third is the real acceleration and velocity. For analysis number 2 and 3, the analysis was made on the setup road grade track, which consists of first is the flat road with left and rightward inclined road, and inclined road with leftward and rightward bend angle. The first analysis is to study the accelerometer and gyroscope output due to orientation of X, Y, and Z. So first, when the y-axis is tilted to the angle of 30 degrees here, the acceleration on y, AY, increase, but AX remains constant to 0 as it does not detect any rotation along the x-axis. But the angular rotation, GY, fluctuate to positive value. In contrast, when the x-axis is at 30 degrees, the AX reduces to negative value, but the angular velocity GY fluctuate to positive value. However, when the z-axis is tilted, is rotate to 30 degrees, it only detects the rotation along the z-axis, but the only force acting on the sensor is the gravity with 9.81 meter per second square. Dual axis is the combination of two single axes, and triple axis is the combination of x, y, and z axis. The acceleration shows a similar pattern, but the angular velocity of x, y, and z fluctuate to positive value on triple axis. Secant analysis is the acceleration due to tip angle which performed on the setup road track. Here we have flat road and inclined road. There is no inclination on any axis, thus the acceleration remains constant, but the inclined road, the AY, increased to positive value. But here we can see that the acceleration is constant as it reaches the peak and moves on the flat road. And the GX shows that the change of device orientation as it reaches the top, and this one is when the device starts to move downward. When the device is turning left, only the GZ of the flat road increases to positive value. For the inclined road, AY increase, and once the device started to drift leftward, AX increased slowly. So this signifies that it is moving upward and changing direction to the left. When the device is turning right direction in flat road, only the GZ reduced to negative value. For the inclined road, AY increased. Once the device started to drift rightward, AX reduced slowly, and this signifies that the device is moving upward and changing direction to the right. Third analysis is to obtain the real acceleration and velocity of a moving vehicle. For the forward direction in the flat road, upon starting to move, the velocity showing an almost zero acceleration, but increase to positive acceleration as it starts to maintain the ideal speed and move in forward direction. For the inclined road, the positive velocity indicates that it is accelerating while climbing up the road. And here, reaching the top, the device starts to decelerate and maintain the speed on the flat surface. For the left turning direction, between 10 to 12 seconds, the device is at a constant positive velocity to slow down and maintain the speed when turning to the left direction. For the inclined road, here we can see that it is slowly decelerate while turning leftward with a bank angle. So here, banking of roads gives a small angle of inclination for a safe turn. And the sharp positive velocity of slope signifies that it is accelerating, once it reached the top of the flat road. For the right turning direction event, the pattern is similar to the previous left turning direction. As for the flat road, on the 6th second, it is accelerating and then decelerate at 12. For the incline road, at the time of 7 to 13 seconds, the device is accelerating upward and then slowly decelerates while turning rightward with a bank angle. It then accelerates once reach the top and start to maintain the speed on the flat surface before decelerates to a full stop. The last analysis is to obtain the real acceleration and velocity on real road vehicle tests. So the first test was made on Pahit Raja to Air Hitam roadway with a speed of 70 to 80 km per hour for like 11 minutes. So it is a straight and flat roadway which has incline road at the exit junction to Tol Air Hitam. Here we can see that the acceleration is mostly constant since the traffic condition is clear, but the red circle describes how the vehicle is accelerating uphill to maximum value before decelerating downhill or coast down and stopped by the traffic light on the exit junction to Tol Air Hitam. The second test route was performed from Air Hitam bus terminal to JPJ Kluang with a speed of 60 to 80 km per hour for about 15 minutes. This roadway has few small curve radius than the first test routes, and the curve roads are frequently followed by braking and turning. Here the red circle shows an event of a sharp U-turn, and after decelerating, there is a sharp positive velocity slope and to achieve a maintained speed on the main road. In conclusion, this project has implemented two methods of evaluation. First is by manual and second is development of motion sensor. For the manual evaluation, method of analysis using Microsoft Excel with aim to identify factor and parameter that give significant effect on the battery consumption. The parameter included are trip distance, speed, temperature, and load factor. The types of test road are highway and roadway, and in the conclusion, when the trip distance, temperature, and load factor increase, battery consumption increase. Here, energy consumption and range of EV can be estimated as well as its energy cost of a ICE car. For the development of motion sensor, the method of analysis using vibration data toolbox with the aim to estimate driving behaviors such as accelerating, decelerating, or heading direction changes. The parameter are acceleration and velocity, and the type of test road are plate road and incline road. For the conclusion, acceleration and velocity vary when the vehicle experiencing a multiple road grade due to the role of inclination axis. So here we can enhance EV driving style based on different road condition. A dashboard to display information of on-road driving battery consumption will alert driver on awareness of eco driving. For the recommendation, first, EV energy usage estimation based on the real traffic and road guidance should be developed, and perform an empirical method to estimate EV's power where the mean and variance of the EV power usage can be estimated for specific speed, acceleration, and grade values. The accelerometer sensor can also be used together with GPS to detect position of moving vehicle and measure speed with better accuracy. Lastly is a human-to-machine interface such as vehicle dashboard indicator that give feedback on EV's energy consumption will directly help EV driver modify their driving style efficiently in order to improve energy efficiency. That's all for me. Thank you very much.